going. Today we're going to talk about orbifolds to begin with. And orbifolds are pretty neat spaces. They're singular spaces, spaces that have curvature singularities, things that in general relativity are fairly difficult to treat correctly. Nevertheless, in string theory, they can be analyzed very nicely. In fact, those spaces are strange, have curvature singularities, and things like that, but they're easier to work them out in string theory than it is to work out the propagation of strings, say, on a sphere. Strings on a sphere is complicated, difficult, you can do it after you work very hard, but strings in orbifolds, that are singular spaces, are very neat. So what are orbifolds? Are spaces obtained by identifications that have fixed points. Spaces that arise from identifications with fixed points. So we discussed identifications last time. We said, for example, if you have the real line x, you could say, let's identify x with x plus 2 pi r. And you can think of it as a transformation. X goes to x plus 2 pi r. One thing is that once you have this thing as a transformation, it moves points from this point to that point to that point. And one important thing is that there's no point that is left invariant by this transformation. It has no fixed points. You take 1 and you get 1 plus 2 pi r. With 2, you get something like that. So in this case, let's consider an identification of the real line, again, the real line, and let's identify x with minus x. Very simple identification. You could think of it as a transformation, t, that takes x to minus x, and you're supposed to identify points after you add them with a transformation. Now this transformation, because acting twice on it, gives the same point that you started with. It's called a Z2 transformation. Basically, the identity and the transformation form this abelian group Z2, which is the integers mod 2, you have two numbers 0 and 1, and that's a simple, it's a bad thing to say a simple group, because simple means something very technical. It's an uncomplicated group. So what happens if you do this? You have the origin here. You're supposed to identify points like this, and you fold this. And basically, your intuition tells you that you got half the space only. So what is a fundamental domain for this identification? Remember, yesterday we said the fundamental domain is a region of the original space in which no 2 points are identified, and every point in the whole space has a representative in it. So a fundamental domain would be this, a fundamental domain, including the origin. So every point must have a representative. So every point on this space is certainly identified with 1 point here, so it has a representative. And no 2 points here are identified with themselves. But there's 1 point that is identified with itself. So there's no 2 different points that are identified. But this point, the identification leaves it fixed. The origin is fixed. So the fixed point is x equals 0. And it is here. And therefore, this is a half line. This is the total space. The orbifold that we obtained, this R1 divided over Z2, we call it. R1 for a line, Z2 by the identification. This is an orbifold, it's a simple orbifold, and it's the half line. And it is the set of points x greater than or equal to 0. And it's a little bit of a singular space in the sense that it ends. So it requires some care. If you're doing quantum mechanics, if you're doing anything in a space that ends, you have to put boundary conditions. If you have to do gravity in a space that ends, it's complicated. You have to beware what's going to happen. So this is the simplest example of an orbifold. And is it clear? Are there any points in this definition or this example that are confusing? Yes?
Just a little bit. Is the R over Z2, are we looking at it as a quotient of groups?
Well, it's
Or
a
just a
quotient
notation?
space, basically meaning that there's an original space. I'm not looking at it as a quotient of groups, although you probably could. No, in this case, but in general, we're going to write these things. We're going to write a big space here and a group of identifications. So let's leave it like that. Yes?
Is the orbifold the same space as the fundamental domain?
In this case, it is, because remember our rule to construct the space that you're going to practice this afternoon. You're going to do orbifold for an hour and a half. It's going to be fun, I think. Remember, the construction of a space was take the fundamental domain, add the boundaries, and implement the identifications that only act on the boundaries. In this case, the boundary is already included. So in this case, the fundamental domain is the whole orbifold. Yes?
Is the fixed point always singular?
Is the fixed point always singular? Yeah, I think so.
I think I would say have a S2 sphere surface. You can cut it half, and you do the identification. Then the two polar points are more or less a fixed point.
I'm not sure what identification you're doing, but
I have a theta and pi, and then
what?
theta and phi.
theta and phi.
I
Yeah.
can phi identify x to x plus pi, for example.
Which angle are you identifying?
I mean the phi,
Yeah.
I can identify each with this plus pi. 180
Yeah.
degrees.
Yeah, you would get half a sphere,
Yeah.
and you would have some strange things there. We could discuss it privately, I think would be better to see if we can get anything interesting there. Let me do an example that is, this looks different from yesterday. What happened? Manual, maybe? Yeah, now it looks like yesterday. No wonder Mark was having all this trouble. Oops. Oh. So let's do an orbifold that is very famous. Consider the complex plane. Like this, and real numbers. And let's consider the transformation T that takes Z to Z times e to the 2 pi I over n, where n greater than equal to 2 is an integer. So here we have a whole complex plane, and we're supposed to identify things after a transformation T. So basically you say Z should be identified with T acting on Z. So to get an intuition of what's happening, you take the real line here and say, oh, this transformation rotates any complex number by an angle 2 pi over n. So here it goes. There's an angle 2 pi over n. And this would be the transformation. Now, since happily this n is an integer, you can imagine that this whole complex plane is actually, there's another 2 pi over n here, and there are more of those, and there's finally another 2 pi over n here. Since 2 pi is the total angle and n is an integer, there's this n pizza slices. Is that right? Just n of this fill the whole space. So the claim now is that this first one is a fundamental domain. A fundamental domain would be the set of points with argument of z. Argument of z is the angle for the complex number is greater or equal than 0 and less than 2 pi over n. That's a fundamental domain. These points will be identified. And then if you wanted to construct the space, you basically now take the fundamental domain, include the boundary, so you include now this line, and implement the identification. So you glue this line with that, and you got a cone. Because this line is being glued to this line together. And this is a cone in which the total angle here is 2 pi over n. And there's a singular point here, the origin, because the origin is the only fixed point. The only fixed point of the identification. Is z equals 0. So there indeed you got a cone, which is a singular space with an angle there and a curvature singularity. And you obtained it as an orbifold. The curious thing about this is that you obtain only a finite set, well, an infinite countable set of cones. You can take n equals to 2, and you obtain the cone with total angle in here pi, as if you would have taken this thing and glued this line with this one and closed the upper half plane. You can take smaller and smaller cones as n becomes larger and larger, but you have a finitely countable set of cones. If you want a cone of irrational angle, you can't obtain it as an orbifold. If n would not be real, an integer, but say, for example, would be irrational, then you go an irrational angle, and you must identify this point to this point. Irrational angle, will never close back to the original point, because irrationals cannot make up a rational. So you go on forever, and every point would have infinite images, and you don't create anything. So if n was irrational, you can't do it. So in string theory, you can solve these cones. These cones can be calculated, but a cone of an arbitrary angle cannot be calculated in string theory. But already this cones is quite remarkable. You can do it. Any questions?
Yes. Can I just clarify the terminology? So the orbifold is the cone.
The orbifold here is the cone. So this is the space, and this is the orbifold. The cone. More questions? Yes?
When you said we can have an infinite number of cones, how is that different from when we had the line we said every 2 pi r we can do a connection? When we then would we have an infinite number of circles in the same line?
No. Here you have if you do this transformation, you got one circle, because the fundamental domain is one thing. When I said an infinite number of cones is when you take n equals 2, you get a cone with 3, 4,
Okay.
all to infinity.
Right.
Yes,
What happens if you include the point at infinity?
louder.
If you include the point at infinity,
Okay, I've included the point at infinity because I've talked about the complex plane. So the point at infinity is rotated. It's not a point. When you have so you're going all the way. If you included the point at infinity in the sense of what is called the Riemann sphere,
yes.
you see the complex plane with the point at infinity forms actually a sphere. It's as if the whole thing, by the time you go far enough, you go to the other side. So you would obtain funny spaces that are sort of, and perhaps they're closely related to what was mentioned before. You would imagine this here, and if you didn't have the point at infinity, you have this sort of cone here that is starting to form at this point 0. But there's a point at infinity, and these 2 points must reach the point at infinity. So in some sense, you got this. So your space would have become some sort of space like this. A little strange. Okay, I did this, and I want to leave for you a little puzzle if you want to think about it. I said if n would be irrational, this would not work. But how about n would be sort of rational? How about z identified with z times e to the 2 pi I m over n, where m and n are relatively prime, and m is n is greater than m, which is in fact greater than equal to 2. So instead of having n equals 7 and you have 2 pi I over 7, what if you have 3 over 7 or something like that here? Do you get more cones or don't you get more cones? What do you get? It's an interesting question. It's interesting because the answer is that it's not a cone with angle 2 pi m over n. That you don't get that. You might think you get that, but it's not that. And probably the best way to think about it is to just do a little experiment. Take some numbers and try to see what you get. In fact, it's very closely related to what is called the Euclid's algorithm for Diophantine equations. It's a very nice question, actually. What do you get from this? But we'll leave it for you to look at. You will do very non-trivial spaces when you consider orbifolds. For example, the sphere, you can't quite do it, the round sphere. But consider a little rectangle and a little rectangle. Here is the first rectangle, and here's the second rectangle. And then use a sewing machine and sew this edge with this edge, this with this, this with this, and this with this. But don't identify the top square with the second. So you make a pillowcase. You put this thing, put the cotton in here, and then put the other one and put it on top. So this is, if I had to draw it, I would probably draw it like this to reflect the fact that you have a square pillowcase. This is topologically the same as a sphere. You blow it with air, stretch it, erase the kinks, and you got a sphere. The sphere, the round sphere, is hard to analyze for strings. Strings move in a complicated way. But in this space, this orbifold, it's easy to analyze. And that's topologically a sphere. So you're getting close to a sphere. and people that do string phenomenology have analyzed this type of orbitals. You will be constructing this kind of orbitals this afternoon. Okay, so now we move on to discussion of strings, but non-relativistic strings. Now, what I'm going to do now may sound elementary. It's not that elementary because we're going to introduce all kinds of little tools that will be necessary tomorrow for the relativistic string. So bear with me a little. And let's go on. Let's see what happens here. Middle and front. This is middle. And rear. Okay. So there is a non-relativistic string. Oops. And the way we imagine it is, to simplify matters, an x-axis that goes from 0 to a, and here is the string doing something, and for the time being, I'll fix the ends. When you consider a non-relativistic string, we consider that there is a quantity called mu naught, which is the mass per unit length, and it has a tension, T naught, which is the tension, which is a force, as it's stretched here. Now we're going to try to write the Lagrangian for small oscillations. What is a small oscillation? Quantitatively, what is a small oscillation? It took me a while to figure out how to express in an equation what a small oscillation is. This is a small oscillation. But this thing, so you would say maybe y should not be big. But this would not be a small oscillation. The derivative is too big. So actually, a small oscillation really, if you go to it, is that dy dx, the position of this string is going to be y. This is going to be the y-axis, y that depends on x and t. Or probably I usually, yeah, y of x and t. Okay, so dy dx is much smaller than 1. So the derivative is always small. If the derivative is always small, then you kind of do this kind of things, and it's pretty good. So this is the condition of small oscillations. Now I want to write an action for this thing, and the action is the potential energy, the kinetic energy minus the potential energy. So what is the kinetic energy? Well, the kinetic energy, I would have to integrate. No, I'm sorry. I'm being very imprecise. The Lagrangian is the kinetic energy minus the potential energy. The action is the integral of the Lagrangian with respect to time. So we're trying to write the Lagrangian. Now, what is the kinetic energy? The kinetic energy is the kinetic energy of each little piece of string. So what I can do is I integrate from 0 to a the kinetic energy, which is 1/2 of the mass, which is mu0 dx, times the velocity squared, which is dy dt, with fixed x squared. Now, what is the potential energy? The potential energy takes a little more work because it is a result of the stretching of each little piece of string. So what is the stretching of a little piece of string? Well, if you have a little piece of string over here, here's a dx, the length, the stretching, the delta L, the stretch, is the square root of dx squared plus dy squared minus dx. So here's dx, here's dy. Well, it's the length of this hypotenuse minus that. If you factor the dx and expand a little bit here, you get dx square root of 1 plus, this is really the partial derivative, dy dx squared, because time is not a matter here. You're differentiating, seeing how it varies with respect to x, minus dx, and to first approximation, this is dx times, you assume this thing is small, therefore you get 1/2 dy dx squared. So that's the little stretching of the little piece of string, and therefore the potential energy is the tension, the force, times the little stretching. That's the energy in the potential accumulated here. So I'll put it under the integral again, minus 1/2 t naught times dx times dy dx squared. So this is, we can write it as 0 to a dx 1/2 mu naught dy dt squared minus 1/2 t naught dy dx squared. And that thing we can call the Lagrangian density, 0 to a dx L, calligraphic L. So first notice what has happened. There's an action. Actions are always integrals of Lagrangians with respect to time. Then there's a Lagrangian, but this time the Lagrangian is not just like the Lagrangian of a particle. You have a x direction for the string, so there's a Lagrangian density that you integrate over x to get the Lagrangian. So that's the same in particle physics. The Lagrangians that Mark was writing this morning were Lagrangian densities. You integrate over d4x. In here, you will integrate over dx, and dt is like a two-dimensional world. So this is L, and we've written it here, and I will write it in a slightly different way. I will write it L of y dot and y prime. By this, and L is this whole thing in the parentheses there. So y dot will mean dy dt, and y prime will mean dy dx. Very good. So let's see. Okay. I could start with this blackboard. I don't mind. Any issue with so far? Any confusion? Any mistake? Any question? No problem. Sure. Okay. So two more definitions. They might seem a little too much, but you see, the fact is that everything I'm doing now in the notation is useful for the string, relativistic string, so bear with me. Let's define a calligraphic P super T, which will be dl dy dot. It's like a momentum. You know that in Lagrangian mechanics, when you differentiate Lagrangians with respect to velocities, that's a momentum. So this is some sort of momentum density. And px, because there's tau, there's the time, and there's the x derivative, so dy prime, here, px will be defined as dl dy prime, And you can calculate them because L is given here. What is dl dy dot? Well, this is y dot, so the derivative cancels the 1/2, and it's actually mu 0 dy dt. And this is minus t0 dy dx. Anyway, all right, we're all set. We have our action, which is the integral from some initial time to some final time, dt, the integral over space from 0 to a, L of y dot and y prime. And now comes the variation. We have to vary to get the equations of motion. This is not hard, but again, it has to be done with some care, and you have to look at some very important points. So first of all, you have to decide what are you varying. Well, in a Lagrangian system, you have dynamical variables, and you vary the dynamical variables. And the dynamical variable here is this one. Variable. Therefore, we must vary that. So we want to calculate, we assume that y will go to y plus some delta y. And I'm suppressing the x and t dependence. Okay, so let's do it. Delta s is going to be, I copy everything, so 0 to a dx. Now, I must vary y. Okay, I have an L, and you know, in a sense, it's better to do it this way because the details of how L is built from y dot and y prime will not matter. And you can apply this to many other examples. So what do we do here? We say, oh, I have to vary y, but y is here and y is there. So what is this? It's dl dy dot times the variation of y dot, whatever that is, plus dl dy prime times the variation of y prime. Now, here comes two things you realize. So two steps now we do. dl dy dot, there's a name so that we don't have to write so much. So we'll write pt. And now the second step is this one. The variation of the time derivative of y means the time derivative of the variation of y. That's all it means. So this is ddt of delta y plus px dd sigma of delta y. As you know, to find equations of motion, you sort of have to separate these guys, and they shouldn't be acted with derivatives. So as long as I don't have to worry, I'm not writing the limits, but I will have to worry for the limits very soon. So what do I do here? Well, then I write dt dx, and I'll write this the following way. ddt of pt delta y plus dd sigma of px delta y. So I replace this by the time derivative of the whole thing, so I have to subtract now the time derivative of this. Minus delta y times ddt of pt. And for this term, I put the total sigma derivative of the whole thing, so I have to subtract the sigma derivative of this. It's a delta y, so it's actually plus dpx dx. And you start to see a nice structure. Look, this looks a little like the divergence of p, dpt, dt, dpx, dx, and some boundary terms that are going to give us headaches. Any?
So you have on the bottom line you have di by di t, and then on the next term you have di by di. What's that?
Oh my God. This is x. X in the string will become sigma. I'm sorry. The x. The x. Y prime. Y prime was defined indeed. Y prime is here. Dy dx. All right. Any other mistakes or questions? Okay, so next step. This is probably the real one. The middle one. Okay. So now we go to the next step. And we integrate by parts. So now I'm going to put all the limits, and there's a second integral here. So the ddt integral can be done. In principle, you get dx from 0 to a, pt delta y evaluated between t final and t initial. For the ddx integral, you get plus integral from ti to tf dt px delta y between x equals a and x equals 0. Because this is an integral ddx from 0 to a. And then we get the rest, which is minus integral dt, integral dx, delta y, dpt dt, plus dpx dx. Okay. That's where we wanted to get. We are now ready to analyze every term, because every term will have an analog tomorrow for the relativistic string, written in almost identical language. I'm going to use a picture here that is going to maybe be a little useful. Ti is here, Tf is here, and here is 0 and a. Well, the domain of interest, we're interested in the evolution of the string that exists from x equals 0 to x equals a, but between times ti and tf. So we're really interested in this region. And it's a rectangle, and we need conditions. There's going to be, here are the points x equals 0 as it evolves in time. Here's the point x equals a as it evolves in time. We drew here that they are fixed, but they need not be fixed. This could be a little hoop here, and this could be moving up and down, but the string still exists from x equals 0 to x equals a. So actually, this line is the endpoint of the string at the origin, and this line is the endpoint of the string at the other side. So these things are very important because they need boundary conditions. You must say, is the string fixed or is it allowed to move? So in these places, you need to put boundary conditions, presumably. And here is the string, the full string at time ti. Here is the full string at time tf. So presumably here you need to put maybe an initial condition and then let it go, or here a final condition and let it go. Final condition. So how do we do this in principle? Well, we have this term, and this concerns the full length of the string at times tf and times ti. This kind of problem, therefore, this term can be dealt with initial conditions for ti and with final conditions for tf. And in fact, in many problems, you can just let the times go to infinity and forget about them. These are not very important. We can postpone dealing with them. Or we can say, yes, I give you the initial condition. This is the way the string looks at time equals 0. And this is the way the string will look at the final time. And then with some peculiar velocity, it will reach it indeed at that time later, and you can put boundary conditions. But those correspond to maybe saying what the string looks at one time and what the string looks at another time. And typically, this is not very interesting. And you don't have to deal with it, except in special cases. So this term, we always can forget it. Unless you're trying to understand what is called the Hamilton-Jacobi properties of Lagrangians, in which you realize that the variations at the endpoints define the momenta associated to the dynamical system, and you can learn something from it, but we don't have to worry. This we have to worry, because this we can't avoid. This is our string in the time of interest, and what it's doing at one end and what it's doing at the other end. So I'd better unpack this term. So what is this term? The second term is integral dt of px at t and x equals a, delta y at t and x equals a, minus px at t, x equals 0, delta y at t, x equals 0. That's all that term from ti to tf. And this term, the action is very important that this term be 0. The action must be stationary. We must guarantee that this term is 0. And this is not something we can forget because we're really interested in what's happening with initial time and final time. Now let me call x star denote either 0 or a, which is an endpoint. Now this is an open string. And we will treat these 2 points independently. I will want this variation to be 0 and this variation to be 0 independently. I don't want to cancel this one with this one, because it's really an open string. One endpoint moves independently of the other. If it were a closed string, there would be no endpoints and this term would not exist. You would say, therefore, a closed string is easier. Wrong. Closed strings are more complicated than open strings. They're subtle in many ways. So this term I wanted to be 0, this term I wanted to be 0. So basically, I'm trying to make something like px of t x star times delta y of t x star equals 0. Middle dot. There we go. Okay, so here finally we get to things. So let me explain this in a way that we discover or understand the basic symmetry between the 2 types of boundary conditions. Symmetry is not apparent at first sight. Well, if you want this to be 0, one possibility is to say, I want the string to do whatever it wants at the end. I want it to be free. Free means that I don't specify in any way how it's going to move or what value it's going to have. So free will mean that I manage to make it the variation 0, not by stating how it moves, but rather by setting whatever that is to 0. So free boundary condition is Px of Tx star equals 0. And you say, oh, okay, looks pretty abstract. But remember what Px is. It's top blackboard. This just means dy dx at x equal x star is equal to 0. Is the condition that the string at the end, the derivative is 0, which is the condition that it's free to move. The Neumann boundary condition, so the free boundary condition is Px equal to 0. If you know what Px is, it's this, which is a Neumann boundary condition. Or the other thing we can do, two things get multiplied to 0. We can demand that this is 0. So this is not a free boundary condition. We can constrain the endpoint by saying that delta y of t and x star is equal to 0. That I don't allow variations of the position of the string at that endpoint. Whatever it is forever. You don't vary it. If you don't allow those variations, this term never occurs. And you don't have a problem. This means that y at t and x star, whatever it is a number. Because you will not vary it. And this is a constant, a number, it's fixed. It's called a Dirichlet boundary condition. Boundary condition. But perhaps more interestingly, it is also the statement that dy dt at x equal x star is equal to 0. The time derivative of that position is 0. And now it looks very analogous to the Neumann boundary condition, except that the Neumann is for space, and this one is for time. In fact, this is the condition that Pt of t and x star is equal to 0. So the Dirichlet boundary condition it's born like it looks very different from the free boundary condition, but when you unpack it, you realize that it's first Dirichlet, and second, it can be expressed as a vanishing derivative, and even as a pt and a px there. And all these things will happen for the string as well. So one last thing I want to say here is that, what probably was the goal of this whole exercise was to find the equation of motion, and that comes from setting that term over here in the second blackboard right there to 0. So what is, I'm going to use this to complete this thing. So the equation of motion, which is the dynamics all over here, except for all these boundary conditions, is dpx, dpt, dt plus dpx dx equals 0. And now, if you want to see what it means, we'll substitute what px and py are. They're up there in the blackboard. So here you get mu0 d second y dt squared minus t0 d second y dx squared. And that's d second y dx squared minus t0 over mu0 with a 1 here, d second y dt squared equals 0. It's a wave equation with velocity t naught over mu naught That's the velocity parameter of the wave. So that's pretty much what you get. A wave propagating there, and that's it. Yes?
And are we ever interested in cases where the boundary terms do not disappear?
When the boundary terms do not disappear, you're not satisfying the equations of motion. So you are, you're really interested in boundary terms that are always zero. The variations should be zero. So, we struggled. We said this, forget it. Don't need to understand it, but you could make it zero. This one must be made zero by either type of boundary condition. So we're going to make them zero.
But is there a reason in principle why it should be zero, or is it just convenience why we take it?
No, it's if you vary the action, it should be invariant. Is already the physical motion is a consequence of the invariance of the action, and if those are not zero, the variation of the action is non-zero. So I have to guarantee everything here is zero. So you see, the variation of the action being stationary also gives you the boundary conditions in the Lagrangian systems. Yes?
So, I mean, just to add on to that point, so does that, is there a case whereby the second and the third term combine to be zero?
Which one? The
Second and the third term?
No, it's really not possible intuitively. Maybe you can construct something extremely cumbersome in which you make something like that. But physically, it makes no sense to cancel an interior variation that governs how the string moves inside with what the endpoints are doing. These are disconnected parts of the problem. So just the same reason, which is that I didn't want to cancel this term with that, which would have been a little more natural. But mathematicians, when they consider this kind of problems, they allow this cancellation. When you cancel them together, you're actually, a physicist realizes you're tying the open string, you're making it into a close. Because that way, the boundary condition in one point affects the other because they're really close. Okay. Last part of the lecture today is the relativistic point particle. So let's see. Maybe I'll just go here and start going up. So you will do a problem for your homework on evolving a classical string configuration. And again, the mathematics is very similar to the one for the relativistic strings, and not all that easy. So relativistic point particle. Point particle. Well, it's even free. So how could it be so hard? A free point particle. What is a Lagrangian? L equal 1/2 mv squared. Quite wrong for relativity because that would allow any velocity, so that can't be right. The momentum from this is the kinetic energies are non-relativistic. The momentum would be dp, the L, dv would be mv, which is the non-relativistic momentum. So this can't be right. So how do you invent the Lagrangian for a three-point particle? Well, you can either do it in a detective way, or you can use special relativity and write something elegant and hope for the best. And that's what we're going to try to do. So here I'm going to imagine space-time. Here's x and t. And I'm going to imagine space and time, and I'm going to imagine this particle moving in some way. And this trajectory, sorry, saying p, but nothing to do with that. Cal p, calligraphic p. Now I want to invent an action. It's sort of, this discussion would be analogous to the way Dirac invented the equation for the electron. He didn't say, oh, well, I need to get this effect on the hydrogen atom and this and the experiment. He said, What is the most elegant equation I can write for a particle with spin? Invented it. That's it. It was right. Here, let's do something elegant. So what does it mean to do something elegant? Let's write something Lorentz invariant. Look, this is a fabulous idea. I wanted to appreciate it because when I appreciated it for the first time, it seemed to me just amazing. If I write an action, the action is going to be based on what the particle is doing. It would be the kinetic energy minus the potential energy integrated or something. But suppose I write it, and I write something that is a Lorentz scalar. That is, any other person, any other inertial observer would look at that particle, compute that thing, and would get the same number. That would be an action that is a Lorentz scalar. Then what will happen? The equations of motion will be Lorentz invariant. This sounds plausible, but it's obvious, and that's the neat part. Whenever the particle moves, everybody computes the action. All of you compute the action. Suppose you're moving in all directions. You all compute the action, and you get the same number. So if we vary the motion of the particle as to get a stationary action, whenever it becomes stationary, since everybody's computing the same action, everybody agrees it's stationary. Therefore, everybody agrees that that motion is physical. Every Lorentz observer agrees that the motion is physical. Therefore, you got a Lorentz invariant formulation. If you say it's doing physical motion, every Lorentz observer says it's doing physical motion. If you take your equation of motion and it's satisfied, everybody will agree. So if I manage to write something that is Lorentz invariant, I have a chance. So what could be Lorentz invariant about this trajectory? The length, the proper time, the integral of ds. Looks like a weird action because most actions that we've been writing are integrals dt of Lagrangian of the position and the velocity. This is integral ds. Well, even the units are not quite right. For an action to have the right units, here it would have to have an m, which is the mass of the particle, and you're missing a velocity, a c. The sign, you may not know what it is, but it turns out to be this one, and we can calculate it quite easily. So presumably, this is the answer. And the only thing I've really put here is the length element. ds is the length element. And the mass times a velocity. And you know why this has the right units, because x times p has the units of h bar, which are the units of action. And this is length, and this is momentum. So, you know, there's no more room for anything except the sign or the coefficient. And then what is that sign or this coefficient? We can calculate it rather quickly. You may remember that we did last time. So the way you go through this is you say, OK, ds, we calculated it yesterday, is cdt. Once you put some Lorentz observer, you fix it, v squared over c squared. So if I want, now I can write this in a more more conventional way. I could say the Lagrangian, well, this whole S would be equal to minus mc squared, square root of 1 minus v squared over c squared dt. So the Lagrangian density, no, not the Lagrangian density, the Lagrangian is minus mc squared, square root of 1 minus v squared over c squared. And if you had been a detective, probably you would have obtained this thing first. But it just came out as the only Lorentz invariant thing you could write. This is interesting because this is a basic exercise you should do. Calculate the momentum, which is dl dv, and you will find the relativistic momentum. Calculate the Hamiltonian, which is p times v minus l, and you will find the relativistic energy. These are very simple calculations, 2-3 lines, but everyone should do them. I want to say one couple more words and leave the rest for tomorrow. There is something quite amazing about this formula for the action of the particle. In addition to the fact that it's very geometrical, is that this parameterization invariant. You have S, the action is minus mc integral ds over the path of the particle. That's all there is to it. I was going to vary this, and I might still vary this, because varying this action, it's not a difficult thing. Just for curiosity, how many of you have varied this action? 1 person, 2 person, 3 person, 4 person. Varying it in a nice way, takes some effort. You know, you do several tries, you do it in a very complicated way, you do it in a better way, you do it in a better way, until you do it in a very nice way. I want to show you that. But the equation of motion that comes when so really what you want to vary is this one, not this one. This one is easy to vary. Lots of square roots, but it's not geometrical. So varying this one in a Lorentz invariant way without breaking into time and things is a challenge, and it's a good thing to do it. Nevertheless, the equation of motion is dp mu d tau equals 0. So what is tau? Well, if you write x mu, the position of the particle, x mu, you can write it as a function of tau. Any parameter. Here is the particle moving. Use a parameter. Tau is a parameter to describe the trajectory. And that parameter, you use it to evaluate the integral. Now, I'm over time, and I'm going to do 1 second more, and we'll be done. ds squared, if you remember, is minus eta mu nu dx mu dx nu. So this is minus eta mu nu dx mu d tau dx nu d tau squared. So this action actually is, if you want to write it with a parameter, integral from tau initial to tau final minus eta mu nu dx mu d tau dx mu d tau times d tau. When I mention varying this geometrically, I mean varying it this way. And this parameter is arbitrary, and this is the equation of motion. dp mu d tau is equal to 0. If you want, read it in the book. I will mention it tomorrow. If you want a challenge, try to derive it yourselves. It is a little bit of a challenge, but not a very serious challenge. Now, if you couple this particle to electromagnetism, as I will discuss tomorrow, you can say again, well, I have to get the Lorentz force. It's a complicated thing. Must be a mess. But actually, it's most elegant answer. Again, there's only one thing you can write. Q over C. There's a vector potential for electromagnetism. And I need to match this index to get a Lorentz scalar. And the only thing to match it is dx mu. So you put A mu, dx mu. And that's the full action of a particle coupled to electromagnetism. It's unbelievable that something like that works. But this shows to you that inventing actions is much easier than inventing equations of motion. These actions are simple things. Scalars, Lorentz invariant, can be easily invented. Nobody would have invented the equations of motion of a relativistic string by writing those equations of motion. You have to do the action. So we'll stop here. We'll see you tomorrow. If you have any questions, come to me, because it's time for a break. You need to rest.